Hi. When we left off last time, we were talking about surface area to volume. And the very last question we were still on is, how do large organisms deal with diffusion? So the point being that if you have a large body like us or a large fish or this heron that's behind me, molecular diffusion is not going to do it. It's not going to get oxygen into your cells fast enough. It's not going to get it's not going to get CO2 out fast enough. It's not going to get all the other things to each cell. And somebody did answer that we use eddy transport, that we use circulatory systems. And that makes sense evolutionarily, because if you look at organisms like Daphnia, which is, a small zooplankton crustacean, and we'll see that in this class, it has a heart, but it doesn't, which is kind of moving stuff around, but it doesn't really have a set circulatory system like veins and arteries like we do. So that's the first step when you're getting bigger, is to just make sure you're moving stuff around inside. And then when you get even larger, then you end up having a heart and a whole circulatory system. But then there's another problem with surface area, and that's getting the oxygen exchange with the environment. So how do large organisms deal with that? Say, how does a fish deal with increasing the surface area for exchange?
Like using hemoglobin?
Hemoglobin is how you transport it, right? Basically from the lungs to in. Oh, wait, here we got, Abigail got it, and Tom. Gills increase surface area available. That's right. And, we have lungs that have alveoli, right? With a massive surface area there with all those little pockets, and we're forcing air in and out. Fish have the gills, and they're forcing water across those gills, and it increases their surface area. So they're basically getting past the surface area to volume problem of being multicellular. Small organisms like single-celled algae, and even multi-cell algae, like we saw Cara, for example. It doesn't have much of a vascular system. It's not a vascular plant yet, and that was the one we saw in the littoral zone of Potawatomi State Lake number 2. It is just basically diffusing throughout, and so it can only get so big and dump off its oxygen when it's photosynthesizing, and bring oxygen in when it needs it for respiration, and bring in CO2 for photosynthesis. So we mentioned that warmer temperatures lead to higher diffusion rates, but how fast is that? And so if we look at this, we're going from about 0.2, right, to 0.4, a little bit above 0.4 in 10 degrees C. So those of you that remember your ecology, this is related to what we call the Q10 in the Arrhenius equation. That is, how many degrees does it take for a doubling of rates? So all rates, biological rates, are essentially dependent upon this. And this is why you get this exponential increase in metabolic rates as you increase temperature, because all the reactions are happening more quickly. The things are diffusing more quickly, right? So the reactants can get there, and the products, if they're waste products, can get away faster. And also, things are jiggling faster, so you've got proteins, they've got an active site, right? So they're either taking 2 molecules and cramming them together, or they're taking 2 molecules and ripping them apart, right? Well, the energy for that is the thermal energy, and so that reaction can happen faster. So the stuff can get in faster, and they can do their work faster and get it done. And these all this will cascade up to the organism's metabolism. At some point you get up here, and things start going to pot. They just fall off. The rates really fall off. What's going on there?
Is it? Oh, somebody was saying something. Sorry.
Oh, go ahead. I started, Emma.
I was saying when things get too hot, then the actual maybe molecules themselves, like proteins, can kind of unwind and become defective.
Exactly. Things start to denature. Lipid membranes start to fall apart. Proteins don't act right. Messenger RNA is held together with protein and bonding. We'll talk about this. It starts coming apart. So in terms of general metabolism, you're not going to have this ongoing up, right? But in terms of diffusion rates, they're going to go up. Good. Okay, question of the day. Which of these statements are true? And go ahead and chat it in there. Okay, so let's go through the statements one by one. Is diffusion faster at colder temperatures in water?
No.
No. Does hydrogen bonding influence diffusion rates?
Probably.
Yeah, probably. I think potentially, Gabriel said. Gabriel, do you want to say why potentially? Or maybe not. Or Trevor? Or anybody? As I'm calling on people, they're not answering. Why might it influence diffusion? The amount of space, sort of. What else is it doing to the molecules? It's pulling them together, right? It's causing them to be sticky. So you're going to have less mixing, essentially, with more hydrogen bonding. So B is correct. Diffusion rates are lower in regions with turbulent flow. That is incorrect, right? Turbulence, remember, is eddy diffusion, right? Or eddy transport, and it's 100,000 times faster or something like that. Surface area to volume ratios are greater for larger objects. No, that was the one that people messed up, right? The bigger something gets, the more volume it has per unit surface area around it, and that's going to influence diffusion. All right, move forward. Maybe.
I actually don't really get why D is false.
So as you make a very small object, right, has more surface area around it per unit volume than a very large object. So if the reason for that is one is that every part of the volume inside a large object is further away. There's more surfaces further away from, right? And then also, if you look at the reaction, the mathematics, right? Surface area is the square of whatever, you know, it could be a cube or whatever, but volume is the cube. So if it's like it's the diameter of a sphere, right, is the volume, right? You get a cube, and the area is pi r squared of a circle, right? So it's always the volume is going up as a cube, and the area is going up as a square of the dimension of the object. Does that make sense?
Sorta.
Okay, that would be worth going back and looking at the textbook again and looking at the slides from the last lecture where I go through the whole example with cubes and the equations. And it shows it for a cubic object, which is easiest to visualize in your head, all right? Does anybody else still have troubles with that? If they do, I'll just go back and show you those cubes. Okay, we've got more than one confused. So here we go. Consider two cubes, one 1 micron and one 1,000 microns on a side, right? So we've got these two cubes, a little teeny 1 micron and one that's a millimeter. So surface area of the small cube, right? It's 1 times 1. So each face of that cube is a square cubic micron, and there's 6 faces of the cube. So the area is going to be 6 cubic microns. I'm sorry, 6 square microns. Then, if you want the volume of that cube, you just multiply the the height by the length by the depth, right? So 1 by 1 by 1. So that's also 6, right? I'm sorry, 1. 1 by 1 by 1, that's 1. So surface area to volume is 6 square microns to 1 cubic micron. In contrast, if it's 1,000 microns along the side, it has 6 million square microns as the surface area, but 1 billion cubic microns, because you're going 1,000 times 1,000 times 6 here. And this one, you're going 1,000 times 1,000 times 1,000. So you're cubing 1,000, right? So the surface area to volume is 6 for the small object and 0.006 for the larger cube, the ratio. So it's simple math. And if you want to pull up the surface area of a sphere, you can do that. And I believe there is even a example in the book on that. But if not, bug me and I'll give you another example if you want to go through that calculation. All right. So we're changing topics here because we're talking about movement of chemicals through water, and now we're going to talk about light and heating of water. And these sort of interact with each other, and then the heating also, the properties of diffusion also are related to it. You can get diffusion of heat. Photosynthesis drives light, is driven by light, so it's really important in all aquatic and terrestrial environments. UV increases are important. We have increases in ultraviolet radiation related to anthropogenic activities, and we'll talk about that. And then water heats up light. So the first point is that light attenuation is logarithmic. And this is an important point. So let's say that we're in a eutrophic lake and we have 1/10 left after 1 meter, right? And by 2 meters, there's going to be 1/10 of that 1/10, right? So there's going to be 100. By 3 meters, there's going to be 1/10 of that 100. There's going to be 1,000, right? This is a logarithmic series, 10, 100, 1,000. So you just think about, if you can think about it that way, it'll stick in your brain that light is attenuated logarithmically. When we get to Beer's law in the lab, it's the same thing. That if you double the length of the cell of the spectrophotometer and you have an absorptive material and you double the length, it's going to increase logarithmically, not just double the attenuation of light. To do this, we use the attenuation coefficient, and in chemistry, that's actually called an absorption coefficient if you're doing spectrophotometry, but they're the same thing. So if you take the natural log of the intensity at one depth, right? Like let's say this is the surface of the lake where we had that probe in the surface of the lake, and then we went down 1 meter. So the maximum and measured the irradiance again, the light again. So we take the difference of the natural log of those, and we take the depth 2 and depth 1. So there's going to be 1 meter between those 2 points in this example, and that would allow us to calculate the light attenuation. So would the light attenuation, would this number be higher in Willow Lake or in Potawatomi State Lake number 2? So Willow was the eutrophic one, right? And the Secchi disk was, I don't know, what was the Secchi disk there? I didn't read it. Half meter maybe? I don't know, quarter meter? And then the Secchi disk in Potawatomi State Lake number 2 was 2 meters. So which one has the greater light attenuation number here? Can either chat it or pardon?
Willow Lake, because it absorbs more light.
Exactly, so it has a higher attenuation coefficient. So within a meter, this would have gone from 1,000 to 500 in 1 meter, and in pot 2, it might have gone from 1,000 to 200. 1,000 to 800 in a meter. So there's more attenuation, so this number would be larger.
Are we going to have to use that equation with all the different like coefficients and stuff? Like, is it important to know what the letters mean?
Yes, it is, and I could either ask it on a quiz, but there's also part of the laboratory where we measured the light profiles, and you have the light intensity at every depth, and you'll be asked to measure the attenuation coefficient at every depth as part of the labs for those. So yes, you will need to know that algebra.
What's the ln I1 and I2 values mean again?
This is a natural log of the intensity of light. So this would be the natural log of that 1,000 that you saw at the surface of Willow Lake. And this would be the natural log at the second depth of the 200 you saw at Willow Lake. Right. If you don't remember natural log, you can just go on your calculator and it says ln on there. There's a button that says ln, and that gives you your natural log.
And what does Z represent then?
Those are the two depths.
Okay.
And so usually this is done in meters per meter, right, for lakes. So the units would be in meters there. And then these can be micromole quanta per meter squared second, which is par, which we measure in. Good, I'm glad I'm getting questions, thank you. Any others? Okay, now I'll express some real data here. Whoops. So we have 3 lakes, and these turn out to be 3 lakes. This is a sewage treatment plant in Oregon. This is one of a very clean lake in Oregon, and this is a mesotrophic lake in the coast of Oregon. And the first one so these limnology plots in lakes and in sediments oftentimes are a little bit weird because the independent variable, right, is put on the y-axis and going down. So it's just like a lake, right, that you just go down with depth. This is not like the normal graph where the independent axis goes along the bottom and it increases along the x-axis. So in this case, the independent variable is here. The dependent variable is on the x-axis. And oftentimes it's labeled on the top. So in this case, we have 100% light at the surface. That's just full sunlight hitting it. And then we're down to almost, I don't know, almost zero at with less than a meter in the eutrophic lake. In contrast, in the mesotrophic lake, we're down to maybe 5% at 6 meters. And the oligotrophic lake, we're down to maybe less than 50% by 6 meters. If we take this scale right here on top of the A panel and we make it logarithmic, all of a sudden these things get linear, right? So we're basically doing a transform. We're taking the transform there. So we show that eutrophic lake, again, now we can see more closely that we're getting 2% of the incoming light at about maybe 0.75 meters here, right? It pulls that scale out. Okay, so that's the first point. 2 major points. Oh, and a third point. I've not defined eutrophic, mesotrophic, and oligotrophic yet, and I do need to do that. So trophic means food, right? And U means rich, meso means middle, and oligotrophic means poor. So this is a sloppy green lake, and this is a nice, clear, unproductive blue lake. And that's what those terms mean. And we'll see them again and again in the.
Will you repeat them? I got the first one, which is U. What's meso? Middle?
Yeah,
What's oligo?
It's poor, nutrient poor, food poor, low.
Do these different classifications like consistently determine how much photosynthesis? Like, are eutrophic lakes defined as always having a bunch of, green water, and oligotrophic the opposite, or is there variation?
Yeah, that's an excellent question, Aaron. There's a lot of work that's been done on that because of lake pollution. But in general, yes, a eutrophic lake is going to be very productive and green, and an oligotrophic lake will be relatively clear and have very low phytoplankton populations. Good. Any other questions? And if not, we'll move on. I get excited about this stuff, but set my watch right, so hopefully I won't go past 11:20 today like I did on Friday. Okay, so one of the things we're doing is Secchi depth, and Secchi depth is a quick and dirty way to get at light attenuation, because the light has to come from the surface, go down to that disk, that black and white disk, bounce off that disk and come up and hit your eye, right? So the greater the attenuation coefficient is, the less light it's going to go, so the more shallow the Secchi depth is going to be. This has been used in a lot of volunteer lake monitoring. You can send people out to their neighborhood lake and have them measure Secchi disk every week if you want, and have them measure it year in and year out. Is your lake getting clearer, or is it getting less clear? So we see then, this is just a bunch of data from different lakes where we had a light meter and Secchi disk, so similar to what we did in Potawatomi State Lake number 2. And those oligotrophic lakes have Secchi disks that can be, this is a really clear lake here, 25 meters. That's almost so far you can't even see that little thing, right? That little disc. And then these lakes, we have some where maybe you can see it for a half meter at the most, right? And there's a really high attenuation coefficients down here.
Is extinction referring to the extinction of light?
Exactly, right.
Okay.
So the higher this is, the more extinction there is, or absorption. It's not consistent with the slide before. I think I call it absorption. It's attenuation. Okay, so attenuation and extinction coefficient are the same thing. Good catch, Emma.
Are lakes classified more with Secchi discs or nutrient content to like classify them as oligotrophic, the different trophic levels?
Yeah, so we'll get to that when we talk about eutrophication, but usually there's a combination of chlorophyll and nutrient content that are used to classify a lake versus its trophic state.
Okay.
Secchi disk can be a little bit confusing because Tuttle Creek Reservoir is very sedimented, right? And so it has a shallow Secchi depth, and it does have a high extinction coefficient, but you don't get much algae growing in there because it's light limited. It can't get enough light to photosynthesize. So that's a case where the light itself doesn't tell you what the actual trophic state is. So that's why you usually use chlorophyll nutrients to determine that. Well, I'm just talking about water and light as just light being some general thing, but different wavelengths are attenuated selectively. So pure water transmits blue light the most efficiently, and chlorophyll absorbs in the red and blue light most efficiently. And cyanobacteria have pigments that can use green light. So we'll see how this plays out. So here's pure water, and the relationship of absorption or transmission actually here versus the wavelength. And we said photosynthetically available radiation is right here from 400 to 700 meters, right? And here's the visible spectrum. You can see lakes really eat, pure water really takes infrared radiation in heavily. And that's why sunlight heats water so effectively. And actually, if people are trying to make a light, well, before we had these LED lights that don't put out any heat, right? They take a really bright light and they'd put a sheet of water between the light and whatever they're trying to get light to, and then move water through that clear filter and just move off the heat. So infrared is really, really important in getting heat in. Now we have a variety of different ones, and I'm going to panic here because I don't remember exactly what everyone is. The first one is just pure water. So we have high transmission in the blue, low transmission in the red. The second one is chlorophyll, I believe. So chlorophyll absorbs heavily at 480 nanometers, and at about 450 nanometers and 685 nanometers. So this is why chlorophyll is green. Most of this is gone because the water, right, either in the atmosphere or in the lake. And then when we see green, that's because the chlorophyll has low transmission in the blue and low transmission in the red, but high transmission in the green. In contrast, we have cyanobacteria, which have special pigments which can absorb in the green. So this flattens all this out. So they still have chlorophyll here and here, but they're also absorbing in the green. This gives them a competitive advantage in low light. So when we went to Potawatomi State Lake number 2, we had a cyanobacterial bloom that was at about, I believe it was at 6.5 meters that we found it. And that was doing well down there because the light it was getting from the surface was green because there's chlorophyll above it, but it's getting some of this light and it can use that. The last of these graphs is just sediments. So sediments actually, inorganic sediments like there are in Tuttle Creek Reservoir, clay sediments absorb more heavily in the ultraviolet and the blue than they do in the red. So that's why they get this brownish reddish look to a lot of lakes that have high sediments in them as opposed to green. So we can look at these classes of lakes and think about how they transmit light differently. An oligotrophic lake, here's the transmission. We see this light coming down, red decreasing fairly rapidly, right? So because pure water absorbs red heat and reddish. And the blue is almost completely transmitted, it stays almost 100% down to 7 meters. In the mesotrophic lake, the green is absorbed a lot more quickly, but the blue and the red are basically affected more because of the chlorophyll. And a eutrophic lake, that even gets more so, where the blue really gets out, the red's out, and then the green is going pretty quickly too because it's all dense there. Okay, so one of the questions I asked that people had a little, I don't know if they had trouble with because we haven't graded it yet, but it's related to the quiz question. If you're lying 7 meters down in a oligotrophic lake, what color does the sun, what color does it look like? If you're in your scuba gear looking up, what color are you seeing?
Probably blue.
Blue, right? That's why lakes are blue, because the light comes in, it hits a particle, scatters off, comes back out. If it's a red light, it's going to be absorbed. If it's blue light, the probability that it gets back out to your eyes is higher. It's the same reason the sky's blue, essentially, right? Because you have water vapor in there that's absorbing red and green more than it's absorbing blue. So the light that's scattered around tends to be scattered back to you through the blue. Mesotrophic lake, well, I said a eutrophic lake. If you're lying in a eutrophic lake and look up, what color are you seeing? And you have to be like in a 1/2 meter deep because there's not going to be any lake left. Anybody? Green, good. We got some green, maybe bluish green too. If there's a cyanobacterial bloom, you're going to see blue-green. That's good too. Yeah, right. So that was that question that I was asking in advance for you to go through and look at this. Excellent. So I just got it why lakes are the color they are. And a lot of you are interested in fish. So why are fish lures the color that
Little tiny question.
Sure.
So on that last one, we had the colorful lines. Is the reason people are saying green? So I see green, but then there's red there too. Is that red just out of the visible spectrum?
You just wouldn't see it. It just wouldn't be as predominant. You know, it's just not going to be predominated as much. You're going to shift over to the blue green, but yeah, you're just not going to see it very much. Yeah, and the infrared is definitely out of the visible spectrum. So part of it is your eyes aren't quite as sensitive to that.
So it matters what's on top, like the fact that that green line is on top of the red line. Is that what they are paying attention to when we answered green?
They're paying attention that there's more transmission of the green. The green had the biggest transmission. So it's the line that's the furthest down here, right? As opposed to blue, which is the furthest line down here.
Okay.
Okay, so why is it that fish lures are the color that they are? So we got the lakes, right? Here's Crater Lake, and it's blue because it's almost pure water. It's really almost distilled water. And light particles can get 10, 20, 30 meters down there, hit light, and then hit some sort of energetic particle that's down there, reflect back. And if it's blue, the chance it gets back out, it gets down there and back is much higher. These green lakes, right, these are green because you've just got a ton of chlorophyll and this cyanobacteria, so it's got kind of a blue-greenish tinge to it. The red light is taken out, but the green light's the most likely to reflect back off. The question though here is, why are fish lures the color that they are on the right-hand side? Can anybody tell me what it is that is the predominant reason for the color of fish lures?
Is it so it could stand out from like the color of the water and what color you're seeing if you're looking up?
Presumably. Okay, so what I've got here is I've got a picture of 3 fish lures, and I've just used Photoshop, right? And I've said, okay, here we have we're down deep in an oligotrophic lake, right? So we've kind of got a mostly blue light. So this is what these look like down there, right? And then I got in a mesotrophic lake, which is somewhat green, right? And this is what they look like down there. And then we get red filter, so it's mainly red being transmitted in this one, and this is what they look like down there. So when there's just red light, there's not much you can see. So let me ask the question. You can see the white easily. What are fish lures designed to attract? And the obvious answer that you're going to say, no, Abigail, you're incorrect. It's not fish. No, it's not predators. Well, yes, they're predators, but what is the main reason for a company to sell fish lures? Who are they trying to attract? People. Good. Fishermen, right? It's the people that are buying the lures they're trying to attract, right? So if they make a nice colorful lure that looks great up on the surface, that's what people are seeing. They're going, oh yeah, that's really bright. I'm going to get that, or that's going to be the thing that does it, right? But that's not necessarily what the fish are seeing, depending upon where you are. So they're not necessarily designed to attract fish. I mean, I'm sure some are, and the movements are, and I know people do these tests and have that do the wiggling of the lure and see if that is attracted to fish in aquarium and those kinds of things. So there's a lot of fish that have red coloration. What happens to that red coloration when you get down deep? Can the other fish sense that? Not as well, somebody said. Yeah, right. So you look at this red filter, right, and there's not very much contrast between red and white. So the thing that's reflecting red and the thing that's reflecting white, they're all kind of the same. So even though these fish might look bright and red when you get them to the surface, it's likely that they're somewhat camouflaged with their markings when they're deep down.